In this video, we give you a brief overview of the most common transformations used in multi-level logic synthesis. Specifically, we will refer to the transformations implemented in SYS, the first and most widely used multi-level synthesis research software tool, developed at the University of California, Berkeley starting in the mid-1980s. We will first introduce how the cost evaluation works, followed by two local transformations, which only modify the internal structure of a node. Then we will look at 5 global transformations, which modify both the internal expressions of multiple nodes and the topology of the graph. The cost operator evaluates the size of a circuit. As we've done before, this cost is estimated using the number of literals. In the example shown here, the total cost is 10, which corresponds to the sum of the literals across the 3 equations. The first local transformation we examine is simplify. This transformation simplifies the logic expression within a specified node, returning its minimal 2-level representation. The goal of this operation is to reduce the overall cost of the circuit. Do note that the expression within a node is not always in 2-level form. In fact, as we will see, some transformations may produce more complex expressions. A secondary purpose of the simplified transformation is to restore the expression to a form consistent with the 2-level model. In this example, we consider a logic expression, f, to simplify. Its current cost is 12 literals. We use Carnot map to synthesize the expression, although any other technique would be equally valid. We first compute the onset of the expression, and then we build the map. Next, we identify 2 implicants, both of which are essential. The final result is the minimal expression, with a cost of 6 literals. The factor transformation is a local operation applied to a node whose expression is currently in 2-level form. It performs factorization by extracting common literals where possible. The goal is to identify sub-expressions that could later be exploited during the global transformations, which will be discussed in the next slides. Since there is no unique way to factor an expression, a heuristic is used to decide which literals to factor out and in what order. The algorithm works as follows. First, we identify the literal that appears most frequently in the expression and factor it out. The resulting expression is split into 2 sub-expressions. The first is the product of the factored literal and the sum of all product terms such a literal was extracted from. The second is the sum of the remaining product terms where no factoring was possible. The same analysis is then recursively applied to both sub-expressions until no further factoring is possible. If multiple literals share the same maximum frequency, a predefined lexicographic order, either ascending or descending, is used to choose which one to factor first. Let's look at an example. We want to factor the following expression associated with node F. Its initial cost is 12. We start by building a table where each row corresponds to a product term and each column corresponds to a literal that appears in the expression. We place a 1 in a cell if the literal, representing the column header, appears in the product term, representing the row header. Otherwise, we place a 0. Next, we sum the 1s in each column to count how many times each literal appears in the expression. We then identify the literal with the highest frequency. If multiple literals have the same maximum frequency, we break ties using a predefined descending lexicographic order. So, we select D. We also notice that C, which has the same number of occurrences, always appears in the same product terms as D. Hence, we can factor both D and C together as DC. Do note that this optimization is applied regardless of the chosen priority order. On the left, we now construct a new table with only the product terms from which DC was factored out. On the right, we include the remaining product terms, which could not be factored. These 2 tables represent sub-expressions that are combined using the OR operation. We now repeat the process on the left table. From this, we extract not B or A, and we stop, since each product term now contains only 1 literal, so nothing more can be factored. In the right table, we can factor B, and due to the same optimization rule used above, we factor also not A. This gives us a new table from this factorization involving all remaining product terms. Since all terms were grouped, we get or 0 on the right. We perform the final factoring on the remaining table, and we stop here. Now we can reconstruct the factored expression, which is DC and not B or A, or B not A and not D or not C. Its cost is 8. It's important to note that while factorization can reduce the literal count, its main advantage lies in revealing common sub-expressions. These can later be reused in global transformations, such as substitution or extraction, potentially leading to a significant improvement in the overall circuit cost. The first global transformation we examine is called eliminate. As shown in the diagram, this transformation takes a node F as input and removes it by replacing every occurrence of the literal F in downstream expressions with the complete logical expression defined in such a node. From a latency perspective, this transformation can have a positive effect. If node F lies on the critical path, removing it reduces the delay by 1 unit. On the other hand, its effect on area can be either positive or negative. Let's assume F is defined by an expression with L literals, and it appears n times as a literal in other downstream expressions. The total change in cost for the circuit is then delta cost equals to n multiplied by L minus n minus L. This value could be positive, that is a cost increase, or negative, that is a cost reduction, depending on how many times F is reused and how large its expression is. To prevent significant increases in cost, this transformation is typically controlled by a threshold parameter, here denoted by S. In that case, the transformation is applied only if the total cost increase is less than or equal to S. Let's look at an example. We want to apply the eliminate transformation to node F in the circuit shown here, using a threshold of 2. We observe that the current total cost of the circuit is 10 literals. We compute the cost variation, which turns out to be +1. Since this value is below the specified threshold, the transformation is accepted. We then rewrite the equations of the circuit description accordingly. Note that the resulting expressions are not yet in two-level form. This normalization can be handled later by applying the simplified transformation. Finally, the total cost becomes 11 literals, as expected, since we had previously computed a cost increase of 1 unit. Now let's briefly analyze how the cost variation depends on N and L. If node F contains only 1 literal, or if F appears only once in the downstream expressions, then the transformation is generally beneficial. In all other cases, the operation tends to increase the cost, which we control by enforcing a threshold. However, subsequent transformations applied to the updated graph may reduce the cost, leading to a net improvement in the final design. The sweep transformation is a special case of the eliminate operation. It removes all nodes that contain only a single literal or a constant. As we've just seen, in these cases the transformation is always beneficial, so no cost threshold is required. Here is an example of a sweep. We start from the following circuit. The initial cost is 5 literals. The sweep eliminates only node K, which contains the literal not A. This results in a simplified circuit with only 2 nodes, and the total cost is reduced to 4, as expected. The substitute transformation takes 2 nodes, F and G, as input parameters. It simplifies the expression of node F by rewriting it in terms of G, if possible. This operation modifies both the internal structure of node F and the graph connectivity as illustrated. If only node G is provided as a parameter, the transformation is applied to each downstream node of G, attempting to rewrite their expressions in terms of G wherever feasible. This transformation reduces the total cost of the circuit by replacing redundant sub-expressions. If F has already been factorized and the expression of G appears as a factor, then the substitute replaces the factored expression with the literal G. The substitute operator enables the reuse of common sub-expressions, which are now computed once and reused by downstream nodes. Here is an example. The node f contains two factors, and the first one matches the expression of g. The initial cost of the circuit is 10 literals. The substitute operator replaces the first factor with the literal g, resulting in a lower cost equal to 9. If, on the other hand, f is a two-level expression, the substitute transformation applies algebraic division of f by g. In particular, we adopt an algebraic model in which Boolean expressions are treated as first-degree polynomials in the variables with unit coefficients. In this model, we perform a division that yields a quotient and a remainder. Thus, f can be rewritten as the quotient f sub g multiplied by g plus the remainder f sub r, keeping in mind that multiplication corresponds to an and addition to an or, once we return to the Boolean interpretation. Let's look at an example. We start with the following two expressions, with a total cost of 9 literals. We now perform the division of f by g. The term a or not b appears c times in the expression on the left. This leaves a remainder of b and c or b, which cannot be further divided by a or not b. So, we stop here, having obtained a quotient equal to c and a remainder equal to b and c or b. These are the final expressions. Note how f has been rewritten and the total cost has improved, now reduced to 7 literals. The extract transformation extracts a common subexpression from two nodes, f and g, and generates a new node to represent that shared logic as shown in the diagram. Like substitute, this transformation encourages the reuse of common parts of the circuit. If the extracted subexpression already corresponds to an existing upstream node in the graph, we reuse that node instead of creating a new one. From a cost perspective, extract can reduce the total number of literals thanks to expression sharing. However, it may increase the latency if the new node lies on the critical path. If both nodes are already factored, the shared sub-expression may be identified as a common factor appearing in both. If only one node is factored, its factors can be used as potential divisors of the other expression. If neither node is factored and both are in sum of products form, a search must be performed to find a common divisor. There are several heuristic techniques for this case, which we won't cover here for brevity. In all three scenarios, the operation may fail if no common sub-expression is found. Let's go through an example. Here is a circuit made of two nodes, one of which is already factored. The total cost is 9 literals. We can see that the factor a or not b is present in both expressions. Therefore, we can extract this factor into a new node k. In this specific case, the total cost remains 9 literals. The last global transformation we examine is called decompose. It takes a node and, by applying Shannon's expansion theorem on k specified variables, extracts 2 to the power of k new nodes. This transformation typically increases both the number of literals and the latency. However, the advantage is that it produces 2 to the power of k simpler nodes, each involving k fewer variables than the original node. These simplified nodes can potentially be reused or substituted in future optimization steps. If any of the newly created nodes already exist upstream in the graph, we simply reuse them instead of creating duplicates. Let's look at an example. We want to apply decompose on node f with respect to variable a producing 2 new nodes, f sub a and f sub not a. The initial circuit has a cost of 5 literals. The node f is then rewritten using Shannon's expansion theorem as a and f sub a or not, a and f sub not a. The expressions f sub a and f sub not a are derived by substituting values in the original expression of f. F sub a is obtained by setting a to 1 and not a to 0. F sub not a is obtained by setting not a to 1 and a to 0. As expected, the total cost increases, reaching 8 literals in this example.